Hello, welcome to AP Calculus, the homework solutions for section 3.7a. We're going to work 15, 16, and 17. On number 15, it says a farmer plans to fence a rectangular pasture adjacent to a river. The pasture must contain 180,000 square meters in order to provide enough grass for the herd. What dimensions would require the least amount of fencing if no fencing is needed along the river? Okay, well, I think it's helpful to draw a picture. So we've got a river here. So this is a lot like our barn example. Okay, so I'm just going to call, it's rectangular, I'm going to call this y, and this x. Now we want to know what dimensions. Okay, so we know that the fencing, I'm just going to call that F, is equal to x plus 2y. And then the area would be x times y, and that's equal to 180,000. Okay, but we're gonna take the derivative of f because we're trying to minimize the amount of fencing. Okay, so we'll make a substitute here. Kind of doesn't matter which one you use, I don't think. We can just say that y is equal to 180,000 over x, and substitute that in right there. So now I have f is equal to x plus 2 times 180,000 over x. So f is equal to x plus 360,000 over x. And one more time here before I take the derivative. We've got x plus 360,000 x to the minus 1. So let's take the derivative. First derivative test, f prime would be 1 minus 360,000 x to the minus 2. So that's 1 minus 360,000 over x squared. We're going to set that equal to 0. So we would have 1 is equal to 360,000 over x squared. Multiply both sides by x squared, and you have x squared is equal to 360,000. So x then would be the square root of 360,000. All right, so 360,000, raise that to the 1/2 power, 600. Should have been able to do that in my head. I was thinking it was 60. All right, so that is going to be 600 meters. So that's our x dimension. Then the y dimension is 180,000 over x. So we can just plug right in 180,000 over 600. Okay, so that's going to be, I believe, 300. 180,000 divided by 600. So that's 300 meters. So our answer would be x is equal to 600 meters and y is equal to 300 meters. So 300 by 600 meter pin. All right, not bad. Hope you were able to get that one. Okay, on number 16, still a similar kind of problem. Hope you remember working these style problems in pre-calculus. Of course, we weren't trying to maximize or minimize, but we have adjacent pins, and we call the book labels that distance x, and the horizontal and the vertical distance y. But so we can also infer that each of these vertical members are y and each of these horizontal members are x. And of course this is number 16, sorry. And we have 200 feet of fencing, so we're going to need an equation that adds up to 200. So that's going to be 4x, because we have 4x here, plus 3y is equal to 200. And then we want to maximize the area. So in terms of x and y, the area of the whole thing, its width is 2x, and its height is y, so it's just going to be 2xy. Length times width, or however you want to say that. Okay, we're going to be taking the derivative of area. That's what we're trying to maximize. So we're going to rewrite this equation. And it kind of doesn't matter which one you substitute for. We can say 4x is equal to 200 minus 3y. So x is 200 minus 3y over 4. So that's x, so I'm going to plug that in for x right there. A lot of the work on these is before you even take the derivative. So we would have 2 times 200 minus 3y over 4 times y. All right, so area is going to be 200, so 2 over 4 is 200 minus 3y over 2. Because 2 over 4 is a half there. Okay, so that's going to be 100 minus 200 over 2 is 100, minus 3 halves times y. All right, so I feel like here that I have maybe done something wrong here. So, all that is times y. So 100, sorry about that, 100y. I was taking the derivative in my head. So yeah, all of this is times y, because there's a y right there, and I wasn't able to solve it. So I can see that we've got to distribute a y across that, right? Because it's 2x. 2 times this is all x, and then times y right here. So distribute the y, and I'd have 100y minus 3 halves y squared. So take the derivative, a prime, that's going to be 100, minus 6 halves, so minus 3y. So 2 times 3 halves would be 3. Set that equal to 0. So we'd have 100 equals 3y. 100 over 3 is equal to our y dimension. Okay, to find the x dimension, we can just plug right back here. So x is equal to 200 minus 3 times 100 over 3 times y. Well, excuse me, 100 over 3 is y. Apologize. So 3 times 100 over 3 there. Over 4. So that's going to be 100 over 4. Right? 200 minus 100 divided by 4 is 25. So our x dimension is 25 feet. And our y dimension is 100 over 3, or 33.33. All right. So there you go, and that's the answer that I gave you on the note sheet. So that worked out. Okay, let's do probably the fanciest one of the three, number 17. So 17, we have three kind of three-dimensional kind of cube-like. So the only cube one is this one, but we have verify that the rectangular solids, I guess rectangular solid is the right word for me to use, shown in the figure has a surface area of 150 square inches, and then we want to find the volume of each. All right, so for part A, we want to do the surface area. So the surface area for figure 1, so that's the far left one, surface area of 1 is going to be 11 times 3. Okay, so the face, that is a height of 11 and it has a width of 3. So 11 times 3, there's 4 of those faces. So times 4. Plus then there's the top and the bottom. So that would be 3 times 3 times 2. So the top and the bottom there. All right, so that's 11 times 12 plus 9 times 18, and that's 150. And that would be in square inches. And then the surface area for the second one, all of the sides are the same since it's a cube. So it's 6 sides times the area of each face is 5 times 5. So 25 times 6 is 150. And the surface area of solid 3 is, there are 4 sides that are 6 times 3.25. So 4 sides, 6 times 3.25, plus 2 sides that are 6 times 6. All right, so just double checking this. That'd be 4 times 6, 24 times 3.25 plus 2 times 36, 150. All right, so there you go. I think the purpose of that was to teach you, remind you how to do the surface area, because you're going to have to come up with an equation in part C. So find the volume of each. So the volume of solid 1, length times width times height. So it's 3 times 3 times 11. And the volume of the cube would be 5 times 5 times 5. And then the volume of the third solid would be 6 times 6 times 3.25. All right, 3 times 3, so it'd be 9, right? 9 times 11, 99 cubic inches. And then 5 cubed, so 125 cubic inches. And then 6 times 6 times 3.25, so 117 cubic inches. Okay, so that shows us even though they all three have the same surface area, they don't all three have the same volume. And part C says, determine the dimensions that would give you a maximum volume. All right, so this one's going to take more of the board, so I'm going to have to go ahead and erase. And I need 2 equations. One for volume. So if I have this rectangular solid, right, we know that for all of them, the top is a square. The top and the bottom are squares. So I can say x and x. I know those two have the same dimension. But the height I could call y. So the volume, the equation for the volume for all of these would be x squared times y. So I've got two unknowns here. But we can, let's see, the surface area, it says, is 150. So for surface area, I have 150 is equal to 2 times x squared, because the top and the bottom are the same, right? All right. Also x and x. 2 times x squared plus 4, because there are 4 faces that are not squares. 4 times x times y. So my drawing is pretty crummy, but hopefully you can see that from the drawing in the book. Okay, we know we're going to have to take the derivative of volume. That's what we're trying to maximize. So I'm going to need to solve, and I think the easiest one to solve for, since there's only one y, let's solve for y and plug that in. So I would have 150 minus 2x squared is equal to 4xy. So 150 minus 2x squared, divide both sides by 4x, is equal to y. And then I'm going to plug that in right here. So volume then is x squared times 150 minus 2x squared over 4x. Okay, I can get rid of one x on the bottom there, and volume then is going to be x times 150 minus 2x squared over 4. Let's distribute the x. Volume is equal to 150x minus 2x cubed over 4. And then I'm going to factor, you don't have to do this, but just to make the number smaller, I'm going to factor a 2 out of each one. So I'd have 75x minus x cubed over 2. So you can see all the work is in the substitution, and the derivative. See, I'm going to even write this a little different. Now we have 75 over 2 times x minus 1/2 x cubed. So I'm just changing it so it's an easy power rule derivative. So v prime finally would be 75 over 2, or 37.5 if you prefer, minus 3/2 x squared. So we're going to set that equal to 0. So let's multiply both sides through by 2 to get rid of the fraction. And so I would have 75 minus 3x squared is equal to 0. So what I did was I just multiplied both sides through by 2. So we'd have 75 is equal to 3x squared. So x squared is equal to 75 over 3, which is 25. So x is equal to the square root of 25 is 5 inches. So y then, I can find y right here. Y is equal to 150 minus 2 times 5 squared, because x was 5, over 4 times 5. So that's 150 minus 50. It's 100 over 20. So that would be 5 inches. So the dimension is y is 5 inches. X is 5 inches. So the maximum volume is 5 times 5 times 5, which I believe was our cube. So the maximum volume for a rectangular solid is you need to make it into a cube. All right, that does it for this video. I will talk to you on lecture 3.7b.